Hello everyone, it's October 16th. Alright, so we're gonna do this for sure. And then this one, look at this. It's not working. The solution that's out there is not working. So I really have to dig into this to figure out like how this one can be done. I mean, at the moment, really have no idea. I did read, so there are 4 solutions here, right? One of them actually works. This one works. I'm gonna upload this one. This one works. None of the other 3 works. So I did take a look, so I'm not quite sure. No, actually, I know exactly why these are not working. So they're kind of a hacking. I mean, I downloaded, but actually I shouldn't download it. Can I just cancel it? Yeah, I think this is good. Right now it is really doing a copy. Now this is the solution that will work. So what I think what it wants is first of all you need to use proxy, and no matter how deep nested those ones are, you just you copy that, but no, it's just copy the address, right? So it'll be fairly fast. You don't really drill down. You only drill down the ones that it does change. So this is kind of what I think the solution will be. So I'm going to try this again today. In fact, I'm going to delete all this. I'm going to do it all over again. But anyway, let's finish today's challenge first. So validate binary tree node. You have n binary tree nodes numbered from 0 to n-1, where node I has 2 children, where I return true if and only if all the given nodes form exactly one valid binary tree. If node I has no left child, then left child will equal to -1, similar for the right. Note that the nodes have no values, and that we only use the known numbers in this problem. So, which is true because it forms one binary tree. This is false because what? It's not a binary tree. Return true if and only if all the given nodes form exactly one valid binary tree. So we want to check if it's a binary tree. Didn't really tell you from where, right? I just say number from 0. So maybe what we can do, I mean, to check if it's valid binary tree, basically just means every node, right? Every subtree has to be binary tree, and this top has to be binary tree, right? And in this case, if you start from 0, you say I'll check 1, I'll check 2, and 1 is a leaf, so 1 succeeds, and 2, well, we check this, and this is empty, so it's also good. So I check this is good, so 2 is good. So 1 is good, 2 is good, this is good. In this case, we start from 0, we check. So I have 1, we check. 1 is actually good, right? So we check. 2, we check. See, that is the problem. This is not a binary tree, right? Because it what's the definition of binary tree? So each node should only have one parent, right? Each node should only have one parent. So for this case, oof. And how about this? This is bad because 0 is, if 0 is a parent, right? 0 is the parent. Going to 1, so 1 should not have a back edge. I mean, this will form a cycle, right? So cycle is no good. Cycle is no, I mean, we can cycle it. That's one way, right? We can cycle it. We can try to see if it is a cycle, and if it is a cycle, it's definitely not good. What about this? What's this? This is, yeah, what about this? I mean, we can say this, we can do. So we kind of have two checks, right? One is, I mean, if it can form a tree, if it can form a tree, yeah, if it can form a tree, then it is a binary tree, right? It is a binary tree because each node has at most two child. So if you can form a tree, a proper tree, which means it doesn't have back edge, and I mean, is this a tree? What's the definition of tree? I mean, we can use the in degrees, and yeah, we can use in degrees for this because each one should only have one in degree. So you're just saying you're going to check for in degree and check for cycle. How do you check for cycle? BFS. No, DFS. DFS the whole thing, right? DFS the whole thing. Not really DFS the whole thing. But you don't know where this starts, right? You don't know who is the root. It didn't tell you which one is the root. Yeah, that's the thing. I want to see if I make changes to this. So instead of 0, I say 1 go to 0, 2. Okay, 1 go to 0 and 2. And then 0 go to -1, -1. All right, this shall still be true. Yep, so it doesn't really, it can be any, you know, any node can be. But I think it still works, right? You just start from any node. We probably need to DP this because we don't know which node is the, yes, we'll DP it. Start from a node. We try to check if this node itself is a binary tree, right? And but how about this? 0 is a binary tree because from 0 what we see is it has to 1. And from 1, you see it doesn't really work, right? It doesn't really work. Okay, I think we have to do in degree because the root has to be yeah, I think in degree might work, right? In degree. So yes, in degree, we can use in degree to find who is the root because the root has 0 in degrees. Right? It has 0 in degree. Everybody else should only have 1 in degree, which means if after we go through everything, there's no root, then that's false. Or if there are nodes with more than 1 in degree, and that's false. So we use in degree to get rid of that, and then we'll have a root. And then the problem just will be, maybe in degree itself can solve the link, the other problem as well, if you think about it. Right, in degree, if we have, right, this is our tree. This in degree is 0, in degree is 1, 1, and then 1. Now, if I go have a back edge, then this in degree become 2. If I go back here, this in degree become 1, then we have no 0. And this, if we go here, then this in degree, which means if we want to form, a cycle, right, that means somebody will have in degree more than 1, and that is wrong. Yes, I think checking in degrees might be sufficient. Might be sufficient. Like it should have one node with 0 in degree, and all other nodes have 1 in degree. Okay, yeah, I think this shall work. Let's give it a shot. So we'll use in degree for this. Now, how do we handle in degrees? We probably need int in degrees, okay, equal to new int n, right? And then for int I equal to 0, I smaller than n, I plus plus, right? So what we're saying is node 0 in degrees. We only need to go in degrees. So if left child I is larger or equal to 0, then in degrees left child I plus plus. And we'll do exactly the same thing for our right child. So we're gonna do right child, okay? And then that's about it. So we calculate the in degrees, and then at the end, we need to count, right? Count the number of 0 and 1. Okay, so we can say int count is new int 3. Okay, then for int I of in degrees, if I is larger than 1, if I is larger than 1, return false. Okay, otherwise count I plus plus, and at the end we shall say return and this is only 2 will be sufficient, right? And at the end we shall say count 0 shall equal to 1, right? Only one node has 0 in degree, right? Which is the root. This is some node has more than 1 in degree. Impossible for binary tree. Okay, let's give this a shot. See if this is sufficient. And honestly, I am not very sure, but I think these can pass. Let's see overall, does it pass? No, it does not. We have something that's wrong. Okay, that's okay. That is fine. I thought this is enough. Apparently it's not. Okay, so 0. Go to left, go to 1, and a 1, go to 0. Oh, and then holy crap. So 0 go to 1, 1 go to 0, and 2 go to 3. 2 go to 3. Yep, this doesn't work, and it has to be connected, right? It has to be connected. Okay, that's fine. So we just need to do another round of how do you check it's connected? Well, you have to DFS this thing, right? You have to DFS this thing. DFS this thing. Yeah. DFS. Yeah, so we use that. Okay, yeah. So we use that. We should actually say this, right? So if count 0 is not equal to 1, okay, then we'll return false. So we can say more than 1 more than 1 possible root, okay. Then we need to know who is 0, right? Then we need to find a root. How do we find a root? We need to find a 1 who is 0. Count.index. Is that the syntax? Hold on. Java array find index of element. Index of. Okay, index of. So we can say int root equals index. No. Count.index. Oh, it doesn't have. No. Jesus, I have to do it. Dart. I don't like it, but that's fine. Int root. Okay, and then for I equals 0, I smaller than n, I plus plus. I might as well do it there. Yeah, I might as well just write it. So in here, in root 0, I smaller than n, I plus plus. If in degrees I is larger than, right? And then we say if in degrees I equal to 0, and then we don't, that's fine. Then root equal to I, and this is going to be in degrees I. Okay, so now we have a thing. Then we can do, let's do BFS, right? Let's do BFS. So we can say set integer. Yeah. So now we need to traverse the tree and make sure that it is that the graph is connected. All right. So integer seen visited equals new hash set. All right. And we're gonna say a q integer q go to q. It's not priority queue. New. Nope. Linked list. All right. And then q.add root. Does it not work? Might not have been initialized. All right, root equal to -1. Okay, then we say while not is empty, q is not empty. Visited dot add root as well, so I can put them together, right? Okay, then we say now pop out. That's the first time we visit, so we don't do it this way. Now I like That's fine. So we can say int current. Okay, int current. Okay, current shall equal to q dot poll. Okay, and we need to know it's left and it's right. Okay. If what should I say? If left child current is large equal to 0, okay, and if visited contains, right, contains left child, which means we have already visited it, return false, right? Already visited left, already visited as a cycle detected. Otherwise, q dot add left child current and visited dot add left child current. Okay, then we do the same thing for right child. So if, say, right child. Okay, once we're done, we'll go back up, blah blah blah. Once we get out, we shall say return visited dot size shall equal to n. If it's not equal to n, then it's bad. So with that, if we try this, yep. Let's put everybody together. Oh, it should be right because the other one will handle. All right, let's try this. Yeah, so it has to go to both, right? Both. Okay, so it's not too shabby. Not too shabby. (1361). Use in degrees to identify the root as the root of a binary tree has 0 in degree. We can also eliminate. We can also detect, right? Detect some of the impossible cases by checking the in degrees. For example, if there are nodes with more than 1 in degree, the binary tree is invalid. For another example, if there is no node or more than 1 node with 0 in degrees, right? The binary tree is also invalid. Now the important thing here is that after the in degree check, we have to perform a traversal of the tree from the root to check 2 more things. Actually, just one thing, to check whether the graph is connected. The graph is only a binary tree if it is connected. It's connected, check whether it's connected and does not contain a cycle. It's only a binary tree if it is connected and has no cycle. ON for all the checks. Well, I shouldn't say ON. It is ON because the edge is only 2 times the n at most. Okay, so let's check the solution. DFS Oh, what the hell? You don't have to start. Cannot be a cycle, must be connected. And how do you check this if you do BFS? Exactly one parent. So you children. Oh, it's more. Yeah, you find root, you have to find root. After you find root, then you go through. Okay, that makes more sense. That makes more sense. Yeah, BFS is the same thing. You have to find root and then do this. Yeah, union find. I'm not gonna use union find for this. Okay, so that's about it. All right, let's go back to this struggle. And let's go here. So, right, what I think, I mean, this one is also not right. Okay, but anyway, we don't need mutated. We don't need any of this. Okay, so what we want to do is collect the keys encountered. That is correct. And if it's this, we'll just do current prop equals this. Okay. We just want to collect the keys during the calls and set them in curve, right? That's it. This is what we want. Now here, this is what's interesting. Okay, this solution is inspired by, right? But it is different. The one from the forum does not work. Probably the online judge has been improved such that those solutions no longer pass. Now this solution, the current solution first captures the exact, okay, the exact what do I say? Captures the chain of object, right? The chain of keys that leads to the update, that leads to the modification of the value. Then we create a clone of the original object, but we don't have to expand on all the elements. We only expand on the keys that lead to the modification, right? All the other objects, arrays, will be a shallow copy of the original, thus avoiding the thus speeding up the cloning process. Yeah, I think that is the key, which means we all have this, right? We can even we can call it mod collect. okay? Partial clone, what kind of partial clone? PC, partial clone, okay? Partial clone. We can just get this, it's fine. Right, we'll do that. The partial clone. The partial clone, once it's done, will give you the actual, whatever is, being cloned. And what you need to do, right? What you need to do is we probably need to define a new function called, you can say clone. Original partial clone. Okay. So we need to create a new one. We can say constant res equals this, right? And what we want is clone the original, right? Just drill through all of them, right? Drill through all of them. And I will return the result. Naturally, we don't even know result is this, right? It depends on the original. And we should say if original is equal to null, or type of original is not equal to object, then we just return original. Done. We don't have to do anything about it. Otherwise, we should say if array.isArray, so original is array, then we say const res shall equal to an array. We'll do that, okay, and then we have the PC, right, at the current, the PC, whichever on the PC we need to keep moving. We should probably return PC instead of return the original, because the value can be changed, right? The value can be changed. Then shouldn't you say PC is null? PC is not an object. You return PC, because I could, right, change a value. So yeah, I should say PC is. Oh, if PC is not. No. I think it's original. If original is not, then we just return PC, whatever the PC is at the current moment. Otherwise, we have to go through all the keys in PC. So we say for let key of object.keys PC. Now we can probably do key value in this object.items, not items, entries PC, right? And we say res parse int k, right? Res this shall equal to clone. Now we probably can say const index shall equal to parse int k, right? Then we can say res index shall to clone original index and value, right? Or do that, and once we're done, we'll return res. Otherwise, const res equal to, can we const res on the outside? Const res. Now let res. So I say res equal to this. Right, now we can do else. Then we can return res. Else is res shall equal to dot 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 original, right? And then the same thing, but not exactly the same. We don't do this. We directly say k and then k. So once we do this, we have PC. Then we say res, okay, const res shall equal to, or maybe we can return clone this the original and partial clone. Okay, something like that. What do you think? I have no clue. Doesn't look right. Oh, I was going to say doesn't look right. I have tons and tons of error. So yeah, this definitely. I thought I copied everything already. Hold a second. Let me put in here. So this is the original one, right? And we have this ridiculous one. Then we can turn this off. I also have this. Okay, and I think this is a different one. Yes, it's a different one. What else? I think this is the same. Yeah. Runtime error. This is a good one. Trouble me a lot. What's about this one? Oh, how about this one? I think that's array 1, 2, 3. Yeah, that's array 1, 2, 3. Okay. That's about all the test case I want to run. Okay, try this. Okay. Come on. Come on. We got a wrong answer. Oh. That is interesting. Oh, we got all the others. 22nd. Huh. A, B, C. A dot B dot C plus 1. Path A. Okay, let's see what the PC look like. Okay, what the PC look like. Okay, PC is correct, right? As PC, we have this set to 2, okay? And now we to do clone. I think the clone has an issue. So we say if original is null, type this is not, or PC is not equal to object. Because PC might be null. So, okay, maybe we say a type of PC is not equal to object. Right? Then we return. All right. Let's try add this. Now I put everybody here. Try it again. All right. I think something is wrong again. Oh. What the hell, man? 25 of 26. 25 of 26. Good Lord. All right. So what I'm curious about is, does our I want to, you know, wait, hold on. Is this one? This is a TypeScript. Oh, I didn't try the TypeScript. All right, let's try. Is this one working? On this, it must have increased the. Dear me. It's pending. What the hell? It's But anyway, while it's pending, we can take a look at what these things do. So we have a giant thing. Everybody is 0. Okay. Everybody is 0. And then man, we can oh, it's just. And then we have these mutate. Oh, come on. What the hell? I just want to see if this solution works. Is that too much to ask? Wow, this one works. Holy crap. This is the real, this is the solution, right? This is the solution. Gosh, but mine doesn't work. Mine doesn't work. They're all doing the same thing, man. All these functions are doing exactly the same thing. Okay, so all these functions are doing exactly the same thing. So we have all these, and then everyone is doing the same thing. X equal to P9. Oh, I see. And you are, and so I need to know if anything gets changed. So that mutation is still needed. This is basically, I'm just hacking this thing, right? At this point, I'm just hacking mutated. It's a false, right? And every time we say mutated equal to true. In fact, I'm not even sure if it's, so I shall even say, because I'm set to this value, and I need to check the original value and this, are they the same, right? We shall say if target, I mean, I can do this now. If target prop is not equal to value, okay? If that's the case, I'll set it to true and I'll do that. Otherwise, I don't do anything, right? And then blah, blah, blah. Once we're done, right, then we say const res will equal to mutated. If it's true, then we have the clone, right? If it's mutated, we have the clone. If it's not mutated, this is the original, right? And then we will mutated equal to false, mutated equal to false, right? We reset it and then return res. So it'll be something like this. Uh-huh. Okie dokie. So now let's try this. I can smell victory. I can smell victory. Then we're getting very close. Very close. Ah, gosh. I'm getting this pending stuff again. It's okay. Let's try it again. Oh, but I think you only get the this. Okay, hold on. This is what I want. Oh, you can only do this much. Oh, it's okay. We will do we'll do here. This is the one. Yep. This is bonkers. Now I have error. What the hell? It's incredible. This is absolutely incredible. That just doesn't work, huh? So which one gets wrong? Dude, this is absolutely bonkers. I think it's one of the earlier ones. It's here? No. No. Where is the... There we go. I think it's one of these. So let's just push these out and then take a look. Is it one of these that's errored? Yep. Which one? I think it's the last one. Output is empty. How? How? The mutated is not mutated. It does mutate it, right? The target prop. Oh, wait. we're setting proxy.a, right? We're setting proxy.a to a value, to 2. The target top prop. I don't understand. Target prop. Ah, this should be not equal to, right? Yes. So mutated is true. Yes, and I'm cloning. Hey, what the hell? Mutated is true, and I'll do this. I'll do the clone. That is bonkers. What the hell? Did I not change some stuff? Oh shoot, I did not change. My bad. PC is not equal to object. I think I just copy and paste things back. I didn't really change the stuff. All right, that was on me. That was on me. Yeah. Okay, one more time. Okay, one last shot. We're close. We're very close. Come on. Come on. Come on. Yes. Yes, come on. Oh my goodness. Oh my goodness. Oh. Finally. Well, this one's pretty hard. This one's pretty. I'm gonna write this discussion. I'll write it later. Basically, I think the main point is I'll explain what this one does. Man, can you put this somewhere else? Like seriously, can you put this somewhere else? Like I don't know. Like every time you do this, let's say maybe we can put this inside. You know, this dot mutated equal to false, and then but then how'd you bind this inside here? That was the problem. Like you don't know. I don't know how to bind it inside. Is there like the bind this? That's a hold on. That's a good question. That's a good question. Let me copy this back. I honestly am not sure. I mean, I'm using this global variable, right? I don't quite like it. Is it possible that clone can be living outside, but I need mutated, which means I want to define this function inside, maybe inside here. Is it possible? Can I define this function inside here? I'm not sure. Yeah, let me try. Did you just delete your test case? Jesus, man. What do I need? I need original. Yeah, let me just copy and paste this stuff. Okay, we got a mutator, we have new object, stop produce, Just don't do all this. Okay, don't do all this. I'll say, can I do, right? Can I do this dot foo? Okay. Yeah, this is basically at this point, it's just practice JavaScript. I say foo is not a function because can I say this dot foo? Oh, this dot foo will work. Okay, so this dot foo. What if I say this dot mutated equals false? Can I, in this function, I mean, I guess this is fine, right? Console.log this dot mutated. I think this is right. Okay. But now we will define a new function inside, right? Bar say function bar console.log this dot mutated does this, and then we call bar. I think this will be wrong. Is undefined, right? So we have to say bar dot bind this. Nope, that's not how it's done. Maybe dot bind this. Nope, that's not how it's done. Function bar. Or maybe I can say const bar equal to this, right? And then we say bar dot bind this. Okay, so maybe I can do it. I can say const set trap equal to target prop value. This dot mutated is true, right? And then const, and then we say set trap dot bind this, and then const get trap equal to target prop. Da, 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 da. Okay. Now when I return, this is going to be set trap, get trap. Oh, can probably put them in one line. Okay. Right. So that's that. Then we don't need this. And clone is clone. We don't need this. Right, and then we can say this dot mutated equals false. Something like this. Let's see. I'll remove this. I'll run it. Throw E. Get partial is not defined. Oh, of course it's not defined because this dot partial is not a function because it should be this and be this dot. Oh, I have to. Okay, I see it. I see it. Get trap dot bind this as well. Okay, let's try this. No? Mutate is not defined. It doesn't work? I bind it, it doesn't work? Huh. How? I already bind this. It's not how it works. Bar, right? This is a function, and I'll bind it, and I can call the trap function. It doesn't work. Get trap. Set get. Mutated is not defined. Oh, I think this is because I forgot this should be this dot mutated. I think it's cooking. I think it's cooking. Yep. Oh man, I like this one better. I like this one a lot better. I probably can do this, you know. Not sure, but just bear with me. Bear with me. I think if we call bind this, it returns a new function as well, which means I don't need this line, I don't need this line. Yeah. So I can make these one together. Okay. Yeah, clone is clone. Oh, I probably can do this clone inside as well. So they're all inside. Yes. Let's do that. Right? Okay, so we'll say this one is this dot clone. And we say this dot clone. This dot clone. Okay, so everything is inside this. Try one more time. Oh, shoot. It should be this dot clone. Yeah, I know. This dot clone. Yes. Yep. Okay. That will be it. I'll write a discussion post for this one. All right. Very happy that we got this one done, but it's not easy. I'll see you guys tomorrow. Adios.